Hello everyone, welcome to Deeksha Karnataka YouTube channel, and today I am going to discuss the chapter Wave Optics, which is a very important chapter for your PU boards. We will see the blueprint in a while, but also this chapter is going to be important in your upcoming FA2 exam. So if you are preparing for your FA2 exam, then definitely watch this video till the end. Also, if you have not yet subscribed to our channel, please don't forget to subscribe to our channel. We are going to bring you lots of important topics for your upcoming PU board, all the exams covered, right? So let us start with the blueprint of this chapter. So as you can see from this chapter, we are expecting two questions. And two questions are mostly two one-marker question. That means one should be MCQ and another one should be your fill in the blanks. Also, we are going to, there are no 2-marker and 3-marker questions that might come in your board exam. So no 2-marker and 3-marker in your FA2. If any 2-marker or 3-marker is going to come, those questions we will cover in the long answer type. Okay, don't worry, we will cover that. So in long answer type, there is one question that is guaranteed to come from this chapter. So if you are struggling with the earlier chapters where the concept is difficult, then this chapter should help you to get 7 marks. So if you watch this video, 7 marks will be guaranteed for you. Now what are all the questions that we are going to discuss? So as usual, we are going to discuss 15 very important MCQs, also 5 fill in the blanks from this chapter, and in long answer type we are going to discuss 3 very important long answer type questions, as well as 2 important numerical questions. Because if you go through your blueprints, you will see that out of the 3 blueprints, 1 blueprint has a numerical question from this chapter and not a theoretical question. So if you see any numerical question coming from this chapter, that is going to be also very important. Now let us start with the MCQs. First, a beam of unpolarized light of intensity I0 is passed through a pair of polaroids with their pass axis inclined at an angle of theta. The intensity of emergent light is equal to. So this is a question based on Malus law. So what is the first polaroid? There are so you have to understand that there are 2 polaroids. First is say P1 and second one say P2. Okay, and their pass axis has an angle between them. So if you take the pass axis, the angle between the pass axis is theta. The light which is falling on this is I0. So I0 is the intensity of the light which is falling on the first polaroid. So what will happen when an unpolarized light is allowed to fall on a polaroid? The intensity of the light which is coming out will directly be I0 by 2. It is always, whenever an unpolarized light is falling on a polaroid, the light after it getting polarized, the intensity becomes half, so it will be I0 by 2, and this is a polarized light. This one is a polarized light. Now when it is falling on the next polaroid, now it is a polarized light, so we can use Malus law, which states that the output intensity, say I, will be given by the incident light, which is I0 by 2 over here, times cos square theta. What is theta? Theta is the angle between the pass axis, so cos square theta, but here you have to take I0 by 2 as your reference point and not I0. Okay, so correct answer will be I0 by 2 cos square theta. So option D is correct for this question. Very interesting, very important question. Now let's move on to the next question. To observe sustained interference pattern on a screen placed at a suitable distance in Young's double slit experiment, which of the following condition or S in plural E/R are necessary? Sources of light should be coherent. That is compulsory, that sources should be coherent for observing Young's double slit experiment. Sources of light should be narrow. Yes, if they are narrow, you are getting a very well observed interference, so this is also very mandatory. Sources of light should be very close. If they are not close, interference pattern will not be visible, so this is also compulsory. So all 3 A, B and C are compulsory to observe sustained Young's double slit. Very important important, sustained young double slit pattern. So if they are not close, you might see interference, but the screen size etc. will be very large, so that is not possible, and you will not get a sustained interference. It will be almost average intensity, so this is not possible. So only when they are close you will get a very clear sharp interference pattern. So now let's move on. So here the answer will be all A, B and C. Diffraction effect is exhibited by only sound wave, only light wave, only matter waves, all types of waves. So diffraction is a property of all types of waves. It is observed in case of sound, it is observed in case of even matter wave. Okay, so electron wave that we will discuss in another chapter, dual nature of radiation and matter. So diffraction is basically observed by all types of wave. So option D, all types of wave, is the correct answer for this question. Now before I continue, I just want to tell you that our KC90 batch 2 is going on. Here we are basically giving you a 90-day crash course for your entire duration of your KCET exam. So it will start right now, it already started, and it will continue till your KCET exam is over. Okay, and as well as not only KCET, we are also covering Comet K exam in here. So those who want to opt for both KCET and Comet K, the price is 8,999, and for KCET only it is 4,999. The price of the batch 1 was 9,999, so it is reduced to 8,999. Moreover, if you add a coupon code, of 500 KC90, you will get over and above 500 rupees off on this price. So when you add this coupon code, you will get this price. Any course you choose, 500 rupees off will be given on this. So don't wait, grab this offer today. The classes have already started, so don't be late. Join today. KC90, here you will get complete class 11-12 coverage. You will get chapter wise PYQs as well as DPPs. You will get KCET, Comet K and PU2 test series absolutely without paying anything extra. You will get live doubt solving. So we will come and discuss all the doubts that you have. Downloadable note and PDF. You will also get exclusive WhatsApp community access. And if you're wondering, so batch 1 students, 92% of the batch 1 students rated this 4.5 and above. Okay, so this is a highly appreciated course of for KCET and Comet K. So don't wait. If your target is to get through a top engineering college, that is your rank should be below 1000, then this is the pathway. So don't wait, join the course today. Now let's continue with our lecture today. If unpolarized light of intensity I0 is passed through a single Polaroid, the intensity of emergent light. So here we have only one Polaroid. So you already know that when unpolarized light of intensity I0 passes through a Polaroid, the intensity drops by 2. So it will be I0 by 2. Correct answer is again option D, I0 by 2. So put that in your head always. Okay, this is a very important concept for PU as well as KCET. Now next question, the phenomena of bending of light at the corners of an obstacle is called diffraction. Bending of light on the obstruction on an obstacle is called diffraction. So when a sharp edge is presented to a narrow beam of light, it bends near the edge. Okay, so ideally according to the rectilinear propagation of light, if light is propagating like this, we should get a light here. If you put a screen over here and complete darkness over here, but in reality you will see that some spot is bright, and that is happening because of the diffraction of light. Light does not travel in a curved path, but it is getting bent and at a sharp edge. It is only happens when the sharp edge is there, and this phenomena is called diffraction. This is the definition of diffraction. So this is diffraction. Now next, according to Huygens principle, the speed of secondary wavelet is twice the size of wave, 0, same as the wave, infinite. So according to Huygens principle, the speed of the secondary wavelet is same as the wave. It is the It is a PYQ. It came in 2024, your PU board exam. Now next, when a point source of light is placed at the principal focus of a thin convex lens, the shape of the emergent wavefront is. So when a point source of light, so here we have a lens and a point source of light is placed at the principal focus. So this is a point source, convex lens. So light after passing through the convex lens, it becomes parallel, okay, because it's a focus. So at focus, if you keep anything, then it will become parallel to the principal axis. So initially the wave pattern was like this. This was the initial incident wavefront, and after it passes through the lens, it becomes parallel. So that means the wavefront will also be plane wave and it will be parallel to each other. So it will be plane wave front. Correct answer is plane wave front. Okay. So in case you see any such questions, try to draw the ray diagram, basic ray diagram, and then try to analyze what is happening, and based on that information try to find out what wavefront it is. Now next, the shape of the wavefront for light coming from a distant star is. So the shape of the wavefront from a light traveling from a distant star, again from a distant star we can assume that the ray of lights are parallel to each other. Okay, that is what we say, that if light object is located at infinity, the light rays becomes parallel. For a distant star, you can assume that the rays are parallel to each other, and based on that fact you can actually say that it's again a plane wave front. Okay, this is a plane wave front. Next, the principle of superposition of waves applies whenever one source of light falls on a screen, one source of light moves across a screen, two or more sources of light illuminate the same point, two or more sources of light illuminate two different points. So principle of superposition means when two waves, obviously two or more waves, when they fall at the same point, what happens at this point, their intensities actually gets added up. That is called principle of superposition based on their phase. It's not a simple addition. Okay, we will see that in through one derivation, but they mathematically they gets added up. We say vectorially they gets added up. So basically when two or more sources of light illuminate the same point, the point has to be same. It cannot be two different points, and we need more than one source. Okay, so two and or more sources of light illuminate the same point. Now let's move on. We will have constructive interference if the path difference is delta x equals to n lambda, delta x equals to n plus 1 lambda by 2, delta x equals to n plus half lambda, delta x equals to n minus half lambda. So we will get constructive interference when path difference is the multiple of n lambda. So n equals to 0, plus minus 1, plus minus 2, plus minus 3. So this is the condition for this constructive interference. So definitely delta x should be n lambda. Now next, to observe diffraction, the size of the obstacle should be of the wavelength. If it should be either lambda or 2 lambda or 3 lambda, slightly more than lambda is preferred. Okay, so it should be of the order of the wavelength. Okay, to observe diffraction, in fact observe interference as well, the slit width that we say, slit width or the size of the obstacle should be of the order of wavelength. If it is too large, the light will not be able to pass. If it is too small, light will easily pass and you will not observe any diffraction. So to observe diffraction, the size of the obstacle should be of the order of the wavelength. Remember this term, of the order of the wavelength, right? Now next question. Two lights each of intensity I0 are used in Young's double slit experiment. The intensity of the interference maxima. If the intensity of the light, both of them are same, the intensity of the light gets multiplied, so it becomes 4I0. The intensity becomes 4I0. For dark pattern it becomes 0. Okay, for dark pattern it becomes 0. Okay, for constructive interference the intensity is becomes 4 times. For destructive interference it becomes 0. Okay, now next, when a compact disc CD is illuminated by small source of light, colored bands are observed. This is due to diffraction. This is due to diffraction. When you illuminate a CD, if you have seen a CD, it was very popular when I was the student like you, but nowadays CDs are almost obsolete. You do not see a lot of CDs. Okay, when we were smaller than you, younger than you, we used to have cassettes. Then cassettes were replaced by CDs when I went to a college. Now then came pen drives. Now it is almost everything is stored in clouds, so we do not no longer use CDs or pen drives, or pen drives are still used a little bit, but CDs and cassettes are obsolete long back. CDs are very rarely used. Okay. So it is diffraction because on surface of a CD there are some grooves, okay, small grooves, and on that grooves light gets diffracted, and that's why we see color. Okay, nowadays you might see a CD in front of a bicycle. Okay, they mount it for the colorful effect that produced by that CD. Okay, if you have seen a CD, please mention that in the comment below. Yes, I have. Yes, I have seen a CD. Please mention that in the comment below. This is a nostalgic moment for me because this was one of the most popular way to collect songs, to watch movies, etc. Right? Now let's move on. While both light and sound show wave character, diffraction is much harder to observe in light. This is because, okay, so one example of diffraction in sound, let me tell you one example. Suppose you are standing behind a wall. Okay, you are standing, there is a wall, you are standing behind, and one of your friend is on the other side of the wall. Okay, so ideally if you are talking in the sense of light, you will not able to talk anything and that will reach to your friend. Okay, but if you talk in sound wave, then definitely the sound wave will reach to your friend who is standing on the other side of the wall. Right? Now why does that happen? This is because sound wave can travel through the barrier. So this is suppose this is the wall, this is where you are standing, and this is where your friend is standing. Okay, now if you talk something, the sound wave will easily travel because it can bend, and the main reason is that the wavelength of sound is much higher. Okay, wavelength of sound is much higher in the order of meter, centimeter or meter. That's why sound wave can easily bend even if the obstacle is little bigger. Okay, but to observe diffraction, in case this is an example of sound waves diffracting. Okay, so if you are wondering, this is an example of sound wave getting diffracted, and you can communicate even if you are not looking at the person. Okay, now for light wave that is not possible because the frequency and the wavelength of light is very small. Okay, wavelength of light is very small, so you need a very sharp and very small object which can actually diffract the light. Okay, one example you can try is razor blades. This is very popular. One experiment is mentioned in your textbook, so you can try that out. Okay, so because light, the wavelength of light is far smaller, it is very difficult to observe diffraction in case of light. Now last MCQ, which of the statements are correct with reference to single slit diffraction pattern? Fringes are of unequal width. So which of the following statements are correct? Okay, actually is correct, it should be is correct. Okay, one of them should be correct. Fringes are of unequal width, fringes are of equal width, light energy is not conserved, intensities of all bright fringes are equal. So if you see the pattern of diffraction of light, you will see that there is a clear spike, very high spike, which is called central maximum, and then the intensity of light gradually decreases and it becomes zero very quick. So these are all secondary maximums. So intensity of light is different for different maximums. Also fringes are of unequal width. The central maximum is most bright and most wide, whereas secondary maximums are not that bright and not that wide as well. So fringes are of unequal width is the only correct statement over here. Okay, so fringe width is this one. So as you can see, the fringe of the bright fringe is maximum, and and central bite fringe is maximum, secondary fringes decreases very quickly. Okay, if you study physics in future, then you will know how to derive these equations, how to use that equation. That will be there in your upcoming journey if some of you chooses to study physics. Now before I continue, I just like to tell you that if you want to get well score in your PU2 exam as well as in your KCET exam, then definitely you have to subscribe to our channel. The link, obviously the subscription button is there, and also you have to join our WhatsApp channel. The link of the WhatsApp channel is given in the description section of this video. Now let me continue with the fill in the blanks from this chapter. A wavefront is a surface of constant, let's see the options, transverse, wave, particle, maximum, phase, diffraction. So only one object which is making a sense, one word which is making a sense. A wavefront is the surface of constant phase. Okay, constant phase. So correct answer will be phase. The light wave, so phase is done. So whenever you are answering, fill in the blanks, try to mark them, and if possible also mark which question you are answering for. So this is already done. This is for 16. This is a way to remember the correct choice. The light waves are dash in nature. Let's see again. Light waves are transverse in nature. Light waves are transverse in nature. Okay. The phenomena of bending of light around the edges of obstacle is called diffraction. It is called diffraction. So these two are also done. Okay. Transverse and diffraction, these two are done. If two waves are coming from two coherent sources superposed in phase, then the intensity of the light at that point is maximum. So when two waves interfere with same phase, the interference becomes the intensity becomes maximum. So it becomes maximum. Phenomena of polarization proves that dash nature of the light waves. Okay, so the phenomena of polarization proves that wave nature of light waves. It proves wave nature of light waves. Okay, in more correct, EM wave. Okay, electromagnetic wave nature of light waves, that should be more accurate. Okay, because only electromagnetic waves can undergo polarization. Okay, sound wave, which is a mechanical wave, cannot undergo polarization. So more accurate should be EM waves. Okay, so more accurate for this option will be EM wave. Okay, so electromagnetic wave nature of light is proved by polarization. Diffraction and interference can occur all types of waves. Okay, all types of waves can undergo interference and diffraction, but only electromagnetic waves can undergo polarization. So that's why it proves the electromagnetic wave nature of light. Now let's move on to the 5-marker question. So first question, two coherent sources of a constant phase difference undergo interference. Obtain the expression for resultant displacement. This is question number 1. Mention the two uses of Polaroids. Give the condition for constructive and destructive interference of light in terms of path difference. Now these two questions can come as a 2-marker question in your FA2. So prepare these two questions as well. Don't ignore that. But this is a 3-marker question, and any one of them will come as a substitute, as a add-on question with them. Okay, so this is a 3-marker. Any one of them will be coming as a 2-marker question, but I have added both questions so that you also get help for your FA2 exam. Okay, so now let's see. Two coherent waves of constant phase difference undergo interference. So let's see two waves. What are the two waves? Say y1 equals to a1 sine omega t. This is a standard equation of light wave. And another wave, say y2 equals to a2 sine omega t plus phi. Okay, so this is the, what is phi? Phi is phase difference, and it is constant, obviously. Okay, now they undergo interference. So if they undergo interference, what happens that you have to add their respective displacements. Okay, so net displacement y should be equals to y1 plus y2. This is the net displacement. Okay, net displacement is y1 plus y2. This is the superposition principle. Okay, or we can say this is a1 sine omega t and this is a2 sine omega t plus phi. Okay, their amplitudes are different in this given case. Now what you have to do, you have to add these two. Now how you can add these two equations? So for that, what we will be doing, we will, for time being, we will keep the first term as it is and we will break apart the second term using sine a plus b formula. Okay, so it will be sine omega t cos phi plus cos omega t sin phi, right? This is the formula for sin a plus b. Now what we will be doing, we will try to take common of sin omega t term and whatever else is left with cos omega t term. Okay, so we will try to take the things which are common. So a1 plus a2 cos phi. Now I am jumping one step. I hope you can understand why I have done that. Okay, so a2 cos phi multiply, when you multiply a2 with each of the terms, okay, so a2 sin omega t cos phi, a2 cos omega t sin phi. Okay, so what we have done, we have taken sin omega t common and we got a1 plus a2 cos phi. Okay, plus a2 sin phi cos omega t. Okay, so this is the two terms that we have received. Now if you substitute this term as r cos alpha and this term as r sin alpha, okay, this is a very common substitution that you do in your integration or differentiation substitution method problems, right? So here what we can write is that obviously r will be common and we will get cos alpha sin omega t plus sin alpha cos omega t. So definitely again we can apply sin a plus b formula and we can write r sin omega t plus alpha. This is the equation of resultant wave, but don't get overboarded. You have to show the value of r as well as alpha. You have to show the value of r as well as alpha. Now what is r over here? So if you take r cos alpha, r sin alpha, if you take the squares of both and add them, you can find the value of r, which will be coming out to be r equals to square root of a1 square plus a2 square plus 2a1 a2 cos phi. Simple, right? So if you add square of these two, if you take the whole square plus whole square of this, that is what we have done, r square sin square alpha plus r square cos square alpha equals to what we got, a1 plus a2 cos phi whole square plus a2 sin phi whole square. You don't need to show this, okay, this is just for your understanding. Now r square can be common, so sin square alpha plus cos square alpha, what is that? Sin square theta plus cos square theta, obviously that becomes 1, so definitely that is 1. So on your left hand side, right hand side, what you got? a1 square plus 2a1 a2 cos theta cos phi plus a2 cos square a2 square cos square phi plus a2 square sin square phi. So if you add them, you will get a2 square is common, cos square phi sin square phi becomes 1. So you get a1 square plus a2 square plus 2a1 a2 cos phi. This is same as vector addition. This is same as vector addition, right? So this one you can remember, or you can do it on the exam hall, but doing this will not give you any extra marks. But if you remember, this is same as your vector addition, that should be sufficient. Okay, you do not need to show this derivation, okay, but if you forget it how to do it, you can remember that, right? So r value is calculated. Now next is alpha. So what is alpha? Sin alpha by cos alpha, that is tan alpha. So r sin alpha divided by r cos alpha, r gets cancelled, you get sin alpha by cos alpha, that is equals to tan alpha, and that is equals to a2 sin phi divided by a1 plus a2 cos phi, same as vector addition. So these two terms are same as vector addition. So if you write this, you will get all 3 marks. Okay, first of all you have to write the equations of the given waves, and then using superposition principle you have to write, using superposition principle, y equals to y1 plus y2, and then you have to simplify this. Okay, right. Now let's move on to the next part. Mention 2 uses of Polaroids. Polaroids are used in sunglasses, car windshields to reduce the glare from reflected light, that is from roads, water surfaces, etc. Now in camera and photographic filters are also Polaroids are used to reduce the unwanted reflection and improve contrast. Okay, so it is used in a camera and photographic filters. If you are someone who is photographic enthusiast, you might have seen that the photographic enthusiasts use a Polaroid filter in front of the camera. Okay, especially when they take a light in the bright condition. Okay, that prevents that safeguards the sensor of the camera. Okay, so that is why Polaroids are used as filters. It is also used in 3D movies. You can mention that 3D movie glasses are also made up of Polaroids. Okay, that is also one of the modern uses. Now condition for constructive and destructive interference. Now based on that, objective questions, numerical questions, both can come. So these formulas are also important. So path difference is given by a delta x equals to n lambda, which is given by n equals to 0, 1, 2, 3, and in terms of path difference, the dark fringes are given by delta x equals to 2n plus 1 lambda by 2, where n is same value. And if you are interested in phase difference, so phase difference is given by 2 pi by lambda into delta x. This is the condition for, this is the path difference. Now if you add respective constructive condition and destructive condition, you will get the respective condition for phase difference as well. This is the phase difference general formula for both cases. You just need to put respective delta x's over here and calculate the actual condition. Right, now let's move on. State Huygens principle. Using Huygens principle, arrive at the law of reflection for a plane wave. This also has come in the past. Let's see. Huygens principle, every point on a wavefront acts as a source of secondary wavelets which spread out in all directions with the same speed as the wave. The new position of the wavefront is the forward envelope, that is the tangent of the surface of this secondary wavelets. Now you can I can explain this later in a separate video, but this is the statement that you have to memorize anyway. Do not make any changes or any mistakes in the statement. Huygens principle and one theory question is very expected from this chapter. If the other question does not come, which is given in your model paper, by the way, this question and obviously the model paper question, which is Snell's law, both are important. So we will do the both derivation. Okay, so first we will start with the reflection. So reflection, what is the main thing? We need to have a mirror. Okay, in case of reflection we need to have a mirror, and we assume that two brothers, 1 and 2, they started from some point at the same time. Okay, and they reached their destination. So when the brother 1 reached over here, the brother 2 reached somewhere here. So this will be our incident wavefront, and by the time the light ray gets reflected and reaches somewhere here, the second light reached over here. So this will be our reflected wavefront. This is called reflected wavefront. Okay, so here we will mark all the incident and reflected wavefronts. Okay, the diagram you have to draw it using scale so that you don't make any mistake, and also put arrows so that it is the light rays that you have to indicate, and these lines are the wavefronts. Okay, so A and B are the incident wavefront. AB incident wavefront, and say this is CD. This is CD is reflected wavefront. Right, so this is how the things goes. Now what you have to show that the angle of incidence is equals to angle of reflection. Okay, so if you draw a normal over here, this will be angle of incidence I, this will be angle of reflection R. Now from geometry it can be shown that if this is angle of incidence, then this angle that it makes with the plane of reflection is also I, and this angle is also R. Okay, so this can be shown. Let me use a different color. So this angle is I and this angle is R. Okay, so this can be shown. We do not need to show that, you just need to mention it that the angle made by AB with the reflecting plane is I, the angle made by the reflected wavefront with the reflecting plane is R. Now you have to show that I is equals to R. For that, what you have to do that, you have to assume that speed of light in the medium is V. Speed of light is V. Okay, one single medium is there, so speed of light is simple only V. Now, so what we said, by the time light reaches from A to D, okay, from A to D, same time light reaches from B to C. So A to D must be equals to B to C, and that should be equals to VT. Okay, because both ray of light take same time. So two brothers started at the same time, but in the path there are some path difference created, and one reaches first and B is yet to reach. B is light 2 is stopped at B. Okay, so this is the incident wavefront, and by the time the light B reaches to C, it already reflected back to point D. So D is our so that's why we said CD is our reflected wavefront. Okay, and so that means the distances should be same because both are equals to VT. Right, now what we will be doing, we have to show that these two triangles are congruent. Okay, ABC and ADC, these two triangles we have to show congruent. Okay, now the order of the side is important in case of congruent triangles. Okay, so we will use ACB and ACD. So from triangle ACB and triangle ACD. These two are the triangles. What we know? We know that AC is common, BC is equals to CD. Okay, so BC equals to AD. Okay, so BC equals to not AD, sorry. Here also it will be wrong. It is CD. Okay, BC equals to CD. Right? So CD, this will be also CD. Okay, so BC is equals to CD and AC is common. AC is common. What else? So AC is common because both triangles have this side AC. What else? If you see that this is a wavefront, right? So this makes an angle 90 degrees. This will also make an angle 90 degrees, right? So angle ABC, so wavefront, remember that wavefront, if there is a wavefront, okay, that is intersecting a ray of light, okay, wavefront will always make angle 90 degree with the ray of light, no matter whatever is the shape of the wavefront. Okay, ray of light, even if it is a spherical, it will always make an angle 90 degree with the ray of light. It is a property of wavefront. Okay, that property we are using over here. Okay, so this angle will also be 90 degrees. So ABC equals to angle ADC. So side angle side. Okay, side angle or side angle side. From that we can say that triangle ACB must be congruent to triangle ACD. Okay, these two triangles are congruent. So what we can say is that therefore angle BAC must be equals to angle DCA. Okay, DCA. Okay, so this is the derivation that we wanted to do. So we can say that I equals to R. This is the reflection of light. So this is hence proved. Hence proved. So this is the derivation of reflection of light. Now next derivation is same. State Huygens principle. Using Huygens principle, arrive at the Snell's law. Snell's law is law of refraction. It is slightly complicated than the reflection one. So here we have a medium which is separating the two media. So this is one medium, this is two medium. Again, two brothers started at the same point, say X and Y. Okay, they started at the same point. During their travel time, they got separated, and by the time X reaches the point A, Y reaches say point say B. Okay, so what is the incident wavefront? Incident wavefront will be this one. Obviously this angle is 90 degrees. Okay, and by the time, now here one important thing, light does not stay in the same medium, light travels to the second medium, right? So by the time B reaches to this point, okay, the light A already reached the second medium and it bends and it reached say at a point B, say C. Okay, B is already taken, so let's say at point C, and this point is say D. So what is the reflected wavefront? Reflected wavefront is same. What is wavefront? By the way, wavefront is the points of same phase. Points of same phase. That means when they started, initially they are at same phase. They had same phase. Now whenever they have started traveling, one is traveling like slightly before the other, and the phase path difference is there, but path difference is there means these two has to have the same phase. Okay, these 2 points has to have the same phase. No matter which medium they travel, phase relation should continue between them. Now, so this is the points of same phase. Now we can say that this angle is angle of incident and this angle is angle of refraction. Okay, this is 90 degrees angle. Okay, this is a 90 degree angle. Now speed of light in this medium say V1, speed of light in this medium say V2. The time taken by light to reach from B to D is T, time to reach from A to C is again T. Okay, so what we can say is that the distance BD and AC are not same, but the time taken by both of them are same. So what is BD? BD will be V1 into T, right? BD is V1 into T. S is equal to VT. S equals to VT. Similarly, AC will be V2 into T. So BD and AC are both calculated. Now we will use the law of triangles to calculate the angle. Okay, we know that in Snell's law the formula starts with sin theta and sin I and sin R. So we will directly calculate sin I. What is sin I over here? So this is a right angle triangle. This triangle is a right angle triangle, right? Now we will apply that and try to calculate what is this sin I. Sin I is perpendicular by hypotenuse. Now if this is the right angle, so this must be the hypotenuse. So AD must be the hypotenuse. And what is the perpendicular? Perpendicular is the side which is opposite to that of the angle. So hypotenuse in this case will be BD. So sin I is BD divided by AD. BD divided by AD. So what is BD? BD is V1T divided by AD. Similarly sin R is AC divided by AD. You can check that out. So here this is the angle R. So opposite side is AC. So AC divided by hypotenuse is AD. So AC divided by AD. So that will be V2T by AD. Now what we will be doing, Snell's law states that we have to show the relationship between sin I by sin R. So we will simply divide them. we will simply divide them and we'll see that AD will come in division, so they will cancel. So we get V1T divided by V2T. Again T cancels, so we get V1 by V2. Now we will cleverly write this as C by V2 divided by C by V1. What is C? C is speed of light in vacuum. C is speed of light in free space. Okay, or vacuum, whatever you are comfortable with, you can write that. You can even write it in air, but here we do not know which medium is air, so that's why we have written it like this. So what is C by V? C by V is the refractive index for that particular medium. This is called absolute refractive index, right? N2 by N1. So N1 is the refractive index of the incident medium, and N2 is the refractive index of the reflected medium. Now do the cross multiplication, you will get N1 sin I equals to N2 sin R. This is the general form of Snell's law. So this is the law that we are trying to prove. So this is also being proved. Easy derivation, no rocket science, only Huygens principle that is mentioned in the previous question. You can write that out. Right? Now let's move on to two numericals. In Young's double slit experiment, the slits are separated by a distance of 0.5 millimeter and the screen at a distance of 1.5 meter from the slits. If the distance of the ninth bright fringe from the central maximum is 1.3 centimeter, calculate the wavelength of the light used. Also calculate the distance of the fifth dark fringe from the central maximum. Now let's see. So here few symbols you have to remember. Small d is the distance between the slits. Small d represents the distance between the slits, which is given by 0.5 millimeter. Millimeter means, again, all the units must be converted into meters because there are a lot of different units. So this will be 0.5 into 10 to the power of minus 3 meters. The distance between the screen and the slits is called capital D. The distance between the screen and the slit is called capital D. Here it is given as 1.5 meter itself, so no need to change that. Okay, now if the distance of the ninth bright fringe from the central maximum is 1.3 centimeter, so bright fringe from the central maximum is given by Yn equals to n lambda capital D by small d. This is for bright fringe. This is for bright fringe. Okay, for bright fringe, any nth order of bright fringe can be written by this formula. From here you can say that lambda is equals to Yn into D divided by n into capital D. Okay, so using this formula you can calculate the wavelength. So distance here mentioned, Yn here is given as, also Yn is given, okay, 1.3 centimeter. 1.3 centimeter, that is 1.3 into 10 to the power of minus 2 meters. Now put all these values over here. 1.3 into 10 to the power of minus 2 into 0.5 into 10 to the power of minus 3 divided by n is ninth bright fringe and d is 1.5. Okay, so you can cancel this. You will get 3 5s are 15 and you get this as 1.3 divided by 27 into 10 to the power of minus 5. So if you divide it, you will get approximately 0.048 into 10 to the power of minus 5, or you can write this exactly as 480 into 10 to the power of minus 9 meter. The unit is meter, all the units are converted, so that means it will be equals to 480 nanometers. So wavelength is calculated. Now next part is still not done. This is not still done. You will still have to answer the second question where it is mentioned also calculate the distance of the fifth dark fringe. So for dark fringe, okay, the distance of the nth dark fringe is given by 2n minus 1 lambda d by 2d. Remember this. Dark fringe, this one is easy. This one you have practiced maybe somewhere in competitive exams, but this one is slightly tricky. So be careful, you have to remember for dark fringe as well. Now let's put the values. Fifth dark fringe means 2 into 5 is 10 minus 1. Lambda here is given as 480 into 10 to the power of minus 9. D is 1.5 and 2 into small d is 0.5 into 10 to the power of minus 2. So if you simplify everything, you should get about 0.65 into 10 to the power of minus 2 meters or 0.65 centimeter. Okay, you can use the calculator because in PU board exam simple calculators are used. 10 to the power values you tackle separately, and then you try to use the other values to calculate the decimal values. Okay, so you will get this as 480 nanometers and 0.65 centimeter as the answer. Now let's move on the last question of the day. In Young's double slit experiment, the slits are separated by 0.6 millimeter and the screen is placed at a distance of 1 meter from the slits. The distance between the first dark fringe and the fourth bright fringe is found to be 0.6 centimeter. Calculate the wavelength of the light used. Very interesting. So first of all, what are all the values given? Small d is given as 0.6 millimeter. Now I already explained, so millimeter means 10 to the power of minus 3 meters. Capital D is given as 1 meter. The distance between the first dark and the fourth bright, actually fourth bright will come first. Fourth bright and first dark is given by 0.6 centimeter. 0.6 centimeter means 0.6 into 10 to the power of minus 2. So this is generally represented by a symbol of delta y. So delta y is 0.6 into 10 to the power of minus 2 meters. Okay, now what you have to calculate? You have to calculate the wavelength lambda. We will use the almost same formulas but in a different way. So first we will see what is the position of the first dark fringe. Position is important. Position formula is same, which is 2n minus 1 lambda d by 2d. Okay, now for first bright fringe you have to put n equals to 1 over here. So n equals to 1 means 2 minus 1. So 2 minus 1 means it will be simply 1. 2 minus 1 is 1. 2 into 1 minus 1, right? Instead of n you have to put 1. So that means it will be lambda d by 2d. Okay, this is the first bright fringe. What about the fourth dark fringe? Fourth bright fringe. Fourth bright fringe is easy, which is n lambda d by simple d. Okay, that is 4 lambda d divided by small d. So what is delta y? Delta y, as you can see, this one is bigger. So lambda d by small d is common and you get 4 minus half. 4 minus half. If you find the difference between them, distance between them, you have to take this one first minus the other one. Lambda d by small d is common. So you get this as, so 4 minus half is 8 minus 1, 7 by 2. So 7 by 2 lambda d by d. Now what we are trying to find? We are trying to find the wavelength. So lambda equals to 2 delta y into small d divided by 7 capital D. Okay, this is the simple formula. So you put that 2 into delta y is given here as 0.6 into 10 to the power of minus 2. Small d is given as 0.6 into 10 to the power of minus 3 and 7 capital D is given as 1 meter. So if you simplify everything, you should get around 1020 into 10 to the power of minus 9. I am not doing the calculation. Approximately it will be this much meter, or it will be 1020 nanometer. Okay, so this is the correct answer for this question. Okay, 1020 nanometer is the wavelength. Again, as you can see, one of the question is taken from your model question paper, one of them is taken from your question bank. So this kind of questions are very common from this chapter, and we are expecting if numerical question comes, that should definitely be based on this formula. Otherwise, theory questions I have already discussed. Now, if you are watching this video, please share this video with your friends so that they can also watch and learn more. I will be back with a new chapter very soon. Till then, bye.